right, so we're going to be talking about graphing absolute values, which we've done a little bit of already, so it shouldn't be anything new. But here's the function that we're going to be talking about, just in its what we call like transformation form is one way to think about that, or sometimes it's called the vertex form of the function. But we've talked about A, H, and K already. Okay, so a lot of this should be familiar to you guys. I just wanted to kind of formalize some of it. Again, we're trying to get you guys prepared to do some of the stuff that we saw that was coming up in the online homework that we want to make sure you guys were able to do. So that's why we went back over lines, and we're doing this again. So the absolute value parent function is f of x equals the absolute value of x. Okay. And so, just kind of grabbing random points on that line, or random points to kind of plug in. So if I say, hey, what's the absolute value of -5, right? So the absolute value of -5 is +5. And so then I could plot the point -5, 5. All right, what's the absolute value of -1? All right, well, that's 1. So I could plot the point -1, 1. Of course, we always like to do 0. What's the absolute value of 0? It's 0. So I can plot the point 0, 0. I can plot what's the absolute value of 3? Well, the absolute value of 3 is 3, so I can plot the point 3, 3. I just need one more point, so something like I don't know, 7 or something like that, or 8. All right, absolute value of 8 is 8, so I can plot the point 8, 8. Okay. To getting an idea of what that function looks like, right? And we should remember that absolute value looks like a V. Okay. So as I go to connect those points, we draw a nice hard V, like it's got a nice hard point on it. So using your straight edge, do that. Really, what you want to think about, if you connect from the top left corner down to the origin, and then from the origin to the top right corner, it'll have the right line for you. This ruler is a little funky. Won't give me exactly what I want. Graph like that. Remember, this point here is called the vertex. We see that it's at 0, 0. Parent function has a vertex at 0, 0. There's something special about absolute values in the way that as they go off in those different directions we want to talk about real quick. Just deals with, if you thought about each half of the problem, each half of the graph looks like a line essentially, right? It's two lines that meet, right? Two rays that meet, form an angle. Well, I want to look at these of each side of the graph. Okay, so remember we talked yesterday about finding slope. We always start on that leftist most point. Okay, so I'm starting here and I'm moving to the point here. And so if I think about, what's my slope here after my rise or my run, so I'm dropping 4, so down 4, and then I'm running 4. So my slope, right, would be -4 over 4, which would be -1 over 1. Okay, so the left side has a slope of -1 over 1. The right side, so again, starting on the lefter of the 2 points, right? So I'm going to start here. I could start at the origin if I wanted. I'm going to start here. I'm going to go to the other point over here. So as I do my rise, looks like I'm rising 5, and I'm running 5. Okay. So the slope on the right side is 5 over 5. Of course, would reduce down to 1 over 1. So we see that the right side has a positive slope of 1 over 1. Okay. And something we're going to take advantage of later is how how to draw that. Just think of that the slope is going to be 1 over 1, or the other side is going to be -1 over 1. Okay. So kind of some properties of the parent function. Okay, anything there you guys need?
No.
All right, so if we want to take that parent function and we want to shift it, okay, we can shift it up and down, we can shift it left and right, right? We've talked about this before. We're going to start off with that vertical shifting, okay? Remember, that's when we add or subtract something onto the end of the problem, okay? So absolute value plus k. So when we add, that'll shift the graph. So they say that up however many units. Okay, so if we do sketch here, we say something like if f of x was equal to the absolute value of x plus 4. Right? So instead of the vertex being at the origin, the vertex is going to be shifted up 4. So it would be at 0, 4. Oops. So something like that. So now it'd be at 0, 4. Bet it. Yeah, I'm disconnected. I knew it. Sorry. So adding will shift the graph up a certain number of units. And then, so on the other side of that, subtracting. So subtracting will shift the graph down however many units. So we're just kind of seeing a quick sketch of what that would look like. So if we said something like the f of x was equal to the absolute value of x minus 2. Okay. So instead of the vertex being at the origin, it's going to be down 2 units. Okay. So that would be at 0, negative 2. Hey Trey, what you doing? Third hour, man. You guys remember doing the up and down shifts well enough?
Yeah.
Okay. So then we had to watch out for the left and right shifts. Right? They kind of tried to mess with us. We saw that happened. We saw that when it looked like we were adding inside the function, that shifts the graph left. That's right. However many units. And so we said to watch out for that. Again, what that will look like, just a quick sketch. So if we had something like f of x equals the absolute value of x plus 5, and then instead of the vertex being at the origin, it shifts at left 5, so it'd be at negative 5, 0. So it would look something like this. And why that happens is because the h value is negative 5, right? But when we say x minus negative 5, well, minus a negative looks like, right, acts like a plus, okay? But the h value is negative, okay? So it just looks like it's adding, but in fact we're subtracting a negative, okay? And so that's why it shifts to the left. Okay. It's the same way when we subtract, or when it looks like we're subtracting, I guess. It will shift us right, however many units. Okay, I got a last sketch here. So we have something like f of x equals the absolute value of x minus 3 or something like that. So subtracting, we'll move it right. So again, instead of our vertex being at the origin, our vertex is going to move 3 units to the right. So it'll look something like this. And again, why that happens is because it's x minus h, right? So when we subtract a positive, it looks like subtraction, right? It looks negative. We say x minus positive 3, it looks like x minus 3. So it looks like a negative number, but it's acting like a positive number. And that's why it's moving it to the right. Okay. So remember we talked about h, right? Let me zoom in a little bit. Right? So remember that h is a liar. Okay? So it's going to do the opposite of what it says it's going to. What you need, Jet? Okay. Anything you guys need there with the shifting up and down, left and right?
No.
All right. So, when math is really used, it's, when you think like somebody who uses math a lot in their job, like an engineer or, a computer programmer or something like that, that the things they want, the equations, the things, or, statisticians and stuff like that, the things they need to do aren't just lying around for them. The equations they want aren't just laying around for them. They have to take the data they have, or the shape that they're trying to create in their computer program, or this, like a curve, like on a or whatever, for trying to build a building. Like these things have to be created. The equations have to be created. Right? They have certain things they want out of it. Right? They want it to be a certain shape, but then they want it to be bent a little bit more this way and starting here instead of over there and stuff like that. So those equations have to be made. Okay. And so real math isn't just having an equation and knowing how to solve it. It's about how to create the equation and be able to manipulate it and use it to find other things that we then want from it. Okay. And so when we are doing problems like this is really more like what real math is used like in real life. Okay. And so what we have here, right, it wants to write an equation with a desired translation based around this particular function, right? And so whatever data or whatever we're up to, we know that it's got a V shape, right? And so what type of equation gives us a V shape? Right? Okay, well, that's an absolute value equation. Okay, or if, if it was like a U shape, okay, what gives me a U shape? Oh, that's a quadratic, right? Oh, this is all falling in a line. What type of equations make lines, right? Well, of course, linear equations do. Right, so we start off with this like basic shape, but then we want to like bend it a little bit more. We want to move it, right? We want to turn it upside down. Like, how do we get those things to happen? Right, so that's what the transformations or the translations do. Okay, so we start off with its basic shape, which is the parent function, and then we start to manipulate it to get it to do the other things we want it to do. Okay, so we're starting off here with just good old f of x equals, dang it, did it again. Can we whack them? Okay, good still. All right, absolute value of x. Okay, and we're going to manipulate it. Okay, and so we want that function to be shifted 2 units to the right and 7 units up. Okay. So I'm just going to name the function g of x. It doesn't really matter. I mean, if you want to call it f again, you can. But we know at its basic level that it's an absolute value problem. So it's going to have absolute value of x, right? And we're going to talk about how to manipulate it, right? And so we see that, it's supposed to be x minus something, right? Well, it says shifted right 2 means that our h value is 2, okay? And so when I subtract a 2, it looks like minus 2, okay? And then here it says move it up 7, which means our k value is 7, positive 7, right? And so with k, right, we trust k, and so we just add 7 onto it. So we see that h is 2, but it looks like minus 2. K is 7, we trust k. Okay? So this is how we would take our absolute value function and shift it 2 units to the right and 7 units up by using this equation. So how do we shift the graph 3 units to the left and up 4 units? If you're going to put in the chat, there's a vertical bar on the key above your enter button. Just hit shift, I think it's /. I'm just going to call this one H. Again, you can call it F or G, it doesn't really matter. So how would we get it to move 3 units to the left and 4 units up? I think you did the last one, Peyton. How would we get to go 3 units left and 4 units up? Right on, Jacob. So the absolute value of x plus 3 plus 4. So seeing that sign switch there on H, and we can trust K. Right? So 3 units left would be a negative 3. We're going to write a plus 3. 4 units up would be a plus 4. We trust that one. Okay. What about that last one? Avery, what do you think? How would we get a shift 9 units to the right and 8 units down? What do you think, Avery? Okay, so on -9, like that. What about the 8 units down? All right. Yeah, then a -8. Okay, good job there, Connor. Saw yours come through. Okay. Good, Jasmine. Anything about writing the equation given certain shifts? Our left and rights always go inside the bars, but we don't trust their sign. Up and downs go after the bars. We do trust them. Okay. Let's flip to the next page. We're going to use ideas to graph a couple functions. Okay. You know, if we were just coming out of this like out of nowhere, right? If just like in 4 weeks I said, hey, graph this function, right? How do you go about doing that? Right? What are the things you need to pay attention to make sure you do it right? Okay. So the first thing I would look at is what's the function, right? What are we talking about? What am I trying to graph? And so I was seeing those absolute value bars. I'm like, okay, well, what absolute values look like? Okay. So this is an absolute value function. And absolute values look like V's. So when I'm done, I better have a V drawn. Okay, whether it's upside down or shifted or squished or stretched, like it better be a V at its heart. Okay. Well, what's happening to this V? I've got -2 here, and I've got this +3 here. All right, and I remember that inside the function, that one always lies to us. That's our left and rights. So this is going to be a right 2. And after the function, those are our up and downs, and we trust that one. So that's going to be an up 3. So we're going to take this graph, this V-shaped graph, and we're going to shift it right 2, and we're going to shift it up 3. Okay. Well, we think about what's the most important part of that graph, right? Where do I start drawing this? All right, and that's our vertex. Okay. Well, where's my vertex supposed to be? Right? Well, it's supposed to be at 0, 0. But we're taking that graph and we're shifting it. So if we're 0, 0, then we shift right 2 and up 3, where do we end up? Where it's supposed to be at 0, 0, but we're shifted right 2 and up 3, where do we end up?
2, 3.
2,
yeah, 3. 2, 3. Okay. So our vertex is now at 2, 3. Right? I mean, this, right? 2, 3. 2, 3. It's not like it's hiding anywhere, right? Only you have to watch out for is that sign, right? There's the 2, there's the 3. You just got to remember that's actually a positive 2, not a negative 2. Okay, it's not hiding from you. It's right there. Okay, so let's put that vertex at 2, 3. Yeah, so I'm going to get rid of that old one. So there's my vertex. Okay. Well, then how do we draw from there, right? So what do we know about these shapes? So remember we talked about, right, it's that V, right? That right side heads off at a slope of 1 over 1. The left side heads off at a slope of 1 over -1. Okay. So as I'm going to draw this shape, right, it hasn't been squished or anything else. It should have the same shape. It should be the same V, just shifted over a little bit. Okay. So as I'm trying to draw the right side, I'm going to go to my vertex. I'm going to go up 1 over 1, up 1 to the right 1, up 1 right 1, up 1 right 1, up 1 right 1, up 1 right 1. Okay. Bunch of points off to the up and right. Now I want to do the left side. I'm going to go up and left 1, up and left 1, up and left 1, up left 1, up 1 left 1, up 1 left 1, off to the left side. So we're seeing that V shape. Okay. So we're using that slope at 1 over 1 on the right, at 1 over -1 on the left. Okay, up 1 left 1, up 1 left 1, or up 1 right 1, up 1 right 1. And that's going to draw those lines. Yeah, that's what this technology, what I do. Technology here does not give me the freedom to tilt the line just the way I want it. It's just a little bit off for some reason. There we go. That worked better. So I used the slopes to draw the rest of the line, right? I found where the vertex was, and then I used the slope to draw the rest of the line, or the line on each side. Okay. Does that make sense how I did that?
Makes sense.
Okay. Does it make sense, Tatum? What about you, Lucas? Does it make sense? Think so? Evan, how about you? Thanks, Maya. You good? I remember when I'd come to class and I'd see Hope, and I'd see Clover, and every once in a while I'd see Peyton and Jet. I remember those days so fondly. Oh well. All right. Well, it makes sense. I want you guys to do this one. Okay. And when you are done, I want you to turn on your camera and you're going to show me your drawing. Okay. Do number 5.
Is this right?
Oh, they changed my view, Connor. Why is it being weird? Sorry. Yes, Connor looks good. Sorry. Computer's not letting me do what I want to do. Yeah, he looks good, man. We also got one. Good, Peyton. Who else got one? Looking good, Jet. What do you mean, Tatum? Is it online? Ty looks good. Stella looks good. Yeah, I'm not sure what you mean by that, Tatum. Is the problem online? Looking good, Hope. I will post them like I normally do. Yeah, when I'm done filling them out. If that's what you're asking. Are you talking about like so that you could write on them like on the computer, Tatum, or just so you could look at them later? I mean, they are like if you were trying to do the doc hub, which would not be great for this. You can. There is that. I did make a post of the packet, but I also do post the filled in notes here every day. So cool. All right, thanks for sharing all you did. Okay. So vertex there at -1, -4. Seeing our slopes off to the right, off to the left. Next thing we look at is what happens when we mess around with A, right? So we've talked about what A and H do, or sorry, H and K do, right? The left and right shifts, the up and down shifts. So I start messing around with A, and again, you guys have done this before, talked about this before. This is something we're going to talk about over and over and over again as we explore different functions throughout the year. So I'm going to start here and draw all three of these graphs on the same coordinate plane here. I want to go to Desmos real quick. What's on the chat? Okay. Thanks, Dawson. Yeah, that's why I offered many times for, and you guys were having trouble getting something. I could have dropped it off. I did that for 2 of your cohorts. So. All right, so there's our absolute value function, right? There's the vertex at 0, 0. You can see it's heading off to the right at 1/1, heading off to the left at 1/-1. So what happens when we say that's 2 times the absolute value of x, right? Here. Okay, so we see that the graph, each side gets steeper, right? We're multiplying essentially like we're multiplying the slope by 2. So now the sides of the V are steeper. We get a sharper, more narrow V, right? And then what happens if we multiply it by 3, right? See that we get an even steeper, right? Sharper V, narrower V. Okay. So looking at that, right, just seeing what it looks like before we draw out here. And go back to the iPad. Okay. So with the red one, the parent function, right, it's going to start at 0, 0. Or if we connect the corners, right, that's all we got to do when we're talking about that. So we go from the top left corner down to the origin. But we're going up 1/1, up 1/1. This is really frustrating. Stupid ruler. It's weird on this side. It seems a little bit more flexible, but sometimes it still blocks in. I get why they do it, but man, it's also frustrating that it doesn't. Whatever. You're wasting too much time. Sorry. Right side should look like that. Left side. Then like that. So we're going up 1, left 1 on the left side. We're going up 1, right 1 on the right side. So just notice how I put the negative on the bottom there very specifically, right? Because I'm going up and then left, right? Well, what happens with y equals 2 times the absolute value of x is that instead of going up 1, right 1 each time, we go up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1. Slope would be 2/1. And going back to the vertex, we'd go up to left 1, up to left 1, up to left 1, up to left 1, up to left 1. And so our slope would be 2/-1. So something like that. A very similar thing happens with the green one, the 3 times the absolute value of x. Start at that vertex, we go up 3, right 1, up 3, right 1, up 3, right 1. And we go back to the vertex, and we go up 3, left 1, up 3, left 1, up 3, left 1. So our slope on the left is 3 over -1. Slope on the right is 3 over +1. So this is called vertical stretching, or vertical stretch. Remember, it appears narrower. All right, we see a sharper V, a narrower V when we stretch it. Right? We talked about that idea with the like silly putty or rubber band, right? When you stretch that silly putty, you stretch that rubber band, it gets skinnier. Okay, so as we stretch these numbers, the graphs start to appear skinnier. Right? And if we had a like y equals 10 times absolute value of x, we'd have like a really, really skinny V. Right? They're all V's. Right? They all have the same shape. It's just they're narrower or wider compared to which way we're looking at. Okay? The parent function is the regular one, the standard, and then as we multiply them by higher and higher numbers, they get skinnier and skinnier and skinnier, more and more stretched. Okay?
Can you keep that for a sec?
I'm sure. You good, Peyton?
1 second.
Okay.
I'm good now. Thank you.
Yep. So let's look at these. I'm going to flip to Desmos again real quick. So we have our parent function. Okay? And we're going to talk about what's 1/2 times the absolute value of x look like. Okay? You see that the V got wider, right, as we did that. And then if we looked at what's 1/4 of absolute value of x look like, and we see that the V got even wider. Right? So the red one being the parent function, the blue one being 1/2, and the green one being 1/4. And so as we compress, right, that was the word we used, the vertical compression, the graphs start to get wider and wider, right? The more they're compressed, the y values are squished down. They start to appear wider and wider. So again, just kind of getting a quick visual on that before we draw it. And we're about out of time here. Oops, that's not what I wanted to share. Good job. So again, just starting at the origin, I'm gonna go up one, right one, up one, right one, up one, right one to all the way to the top corner. Up one, left one, up one, left one, all the way to the top corner again for that parent function. So to get it close enough here, it was a little more friendly that time. And the slope was 1 over 1. Slope over here was 1 over -1. So on the half, what we're going to do, go back to the vertex, so 0, 0. We're going to go up 1, right 2, up 1, right 2, up 1, right 2, up 1, right 2, up 1, right 2. So our slope is 1 over 2. Go back to the vertex, we're going to go up 1, left 2, up 1, left 2, up 1, left 2, up 1, left 2, up 1, left 2. So our slope would be 1 over -2. Okay. So I'm looking at that number, right, out in the front of the, right, it's 1/2 absolute value of x. And so the right side has a slope of 1/2. The left side has a slope of -1/2. And the other one was 1/4 absolute value of x. So we go to the vertex and we're going to go up 1, right 4. Up 1, right 4. So this right side would have a slope of 1/4. Go back to the vertex, up 1, left 4. Up 1, left 4. So the left side have a slope of 1/-4. You can see that by decreasing that slope, right, it makes the V look wider. Right? It makes the V much flatter. So it looks wider. So we're compressing the Y values. It's called a vertical compression. Okay? It appears wider. Yeah, vertical compressions appear wider. So just kind of like wrapping that up there at the bottom. Okay? It says the y coordinate of the parent function is being stretched. Let me change colors here. If the absolute value of a is greater than 1. So if those a, the size of the number, right? We saw 2 and 3. Those numbers are bigger than 1. Okay? That made the graph stretch. Or it's being compressed if the absolute value of a is between 0 and 1. Right? Those fractions, right? 1/2 and 1/4, those are between 0 and 1. Okay? So numbers smaller than 1 give us compressions. Numbers bigger than 1 give us stretches. Okay? Again, we've talked about all this before, and it shouldn't be new. We're just seeing it again, trying to really formalize it for you guys. Okay? I don't know why my camera turned off. Anything about the stretching and compressing that's blowing your minds at the moment? I want you guys to try a couple of the problems on the homework. Again, you're not going to be finishing it because we didn't. We're going to finish this next page of notes Monday. What I'd like you guys to try on the homework for the weekend, I want you to start with 1 and 3, and then 6, 7, and 11. Okay, 1, 3, 6, 7, and 11. I want you guys to try those. We'll finish up the notes on Monday, and we'll finish up the worksheet on Monday. Okay.